Hi, good afternoon, Chemistry 12. This is Mr. Chan. And today what I wanted to do was talk about something called quantitative equilibrium, or KEQ. Now, recall back when we were doing graphing equilibrium, and let me just get this out of here. When we were graphing our Le Chatelier shift, remember we had some questions. Why did I put the reactants on the top and products on the bottom? And remember my answer was I felt like it. And then when the equilibrium shifted back, recall I said, it went down one square while products went up half a square. Why did I choose the why did I choose the full square? Again, remember I said because I felt like it. But what we're going to do today is we're going to actually talk about how we can mathematically calculate how much the equilibrium will go down or go up by, as well as what goes on the top. Is it the reactants or the products? So that's something we're going to be focusing on today. So that is what we're talking about, quantitative equilibrium. Now, if we were to consider the following reaction, AX plus BY gives you CZ, where A, B, and C are the coefficients, and X, Y, and Z are the substances. When we take the ratio of products to reactants at a given temperature, a constant value is achieved at equilibrium. And this is called our KEQ, okay, or equilibrium constant. So simplistically, if we take the ratio of products to reactants at equilibrium, we'll always get a constant value, and that is called the equilibrium constant, or KEQ. Now, one thing for you to be aware of is this has been experimentally determined. So what is KEQ? So if we take the equation on the top, what you have is you have the concentration of Z, which is the products, raised to the power of its coefficient, indicated by C, divided by the concentration of X, raised to the power of its coefficient, multiplied by the concentration of Y, raised by the power of its coefficient. Okay, so simplistically, again, you could think of it, this is just, you could think of it, KQ is just the concentration of your products divided by the concentration of the reactants. Okay, now a couple of things, let me give you an example of what I mean. So let's say we had this equation. Let's say we had, oh, I don't know, 2NH3 is in equilibrium with N2 plus 3H2. If we were to ask for the equilibrium constant, it would be KEQ is equal to the concentration of N2, concentration of H2, raised to the power of its coefficient, in this case of 3, divided by the concentration of the products, the concentration of the reactants, raised to the power of its coefficient. Now, you might say, okay, Mr. Chan, you have that. What if we were to flip the equation? What if we were to say, well, no, what we have is we have N2 plus 3H2 and in equilibrium with 2NH3. Okay, so we would have the KQ is equal to the concentration of NH3 power 2 all over concentration of N2 concentration of H2 raised to the power of Q. Now, one thing you notice is the equation is flipped. So what happens is this, the KEQ value from the top equation to the bottom equation, the value is flipped or inverse for the reverse equation. So let's say if I said, oh, 2NH3 goes to N2 plus 3H2, if the KEQ was a value of 2, what would be the KEQ value for the reverse? And so instead of doing any type of calculation, we just flip the 2 into 1 over 2, which is 0.5. So that's what I mean by flip. It's an inverse for the reverse equation. Now, another option would be, what if I doubled the equation? What if I doubled the concentration? So, sorry, doubled the coefficients. So, let's say I have 4NH3 is in equilibrium with 2N2 and 6H2. Now, how would that work? So then I would go, okay, KEQ, and I'm just going to call this double, is equal to concentration of N2 squared, H2 to the power of 6, all over concentration of NH3 to the power of 4. Now, how does this equation relate back to the original equation here? Okay, so I'm going to say, can I rewrite this equation into, you have N2 H2 to the cubed all over NH3 squared. Can I do that? So notice this N2 concentration times H2 concentration raised to the power of 3. If you take a look at that, it's exactly the same as what you have here. So what I can do is then I can say, okay, KEQ for the, I'll quote, double, what I mean is double the exponents, is equal to KEQ of the original exponents all squared. So if we went back to the equation and said, oh, if for this value, the KEQ is 2, if I were to double the coefficients, what would the KEQ value be? If I double the exponents, it's just square of the original KEQ. So I would say KEQ for double the coefficients would be 4, would be 2 squared, which would be 4. Okay, so that is something for you to be aware of. Let me see, do I have my worksheet here? Ah, yes, I do. Lovely. Okay, now, oopsie. Couple of things about KEQ. For KEQ calculations, temperature must be constant, okay? And the concentrations of reactants and products need to be in molarity or partial pressures. Now, for those of you who did AP, partial pressures, okay? You should know what partial pressures is. This is part of AP. So you should know it as AP, in AP, okay? But all of you should know its molarity, okay? But for those of you taking AP, you need to know about partial pressures as well. Now, pure liquids and pure solids are not included in the KEQ expression, but gases and solutions are. Why? Is because Gases and solution concentrations can change, but pure liquids and pure solids have a constant concentration. All right, now let me give you an example from the worksheet here. So all of you should have the worksheet. And let me give you an example of worksheet number 1. It says at 773 degrees Celsius, a mixture of CO, H2, and CH3COOH was allowed to come to equilibrium, okay? The following equilibrium's concentrations were then measured. Calculate the KEQ for the reaction. Now, in this case, a few things you can be aware of. It says was allowed to come to equilibrium, and the equilibrium concentrations were ... Okay? So in this case, it's key to make sure you understand how to read the questions, because looking at the questions will help you figure out what process you need to use. So in this case, all I need to do is, if I were to do this question, I would go, okay, KEQ, I'll call this number 1. You have concentration of CH3OH all over concentration of CO, concentration of H2 all squared. And so what you get here is you get 0.00261. Then you have CO is 0.105. And here would be 0.25 all squared. And then you punch it into your calculator. If I do that, 0021, 261. I get an answer of 0.398. Okay. Now, if you check your answer on the very bottom, we scroll down, don't get dizzy. Okay, yeah, 0.398 right here. All right. Now, in terms of the units for equilibrium constant, all right, at this point in time, there is no units. All right, what it is, because it is a ratio. Okay. Now, will life be this easy? The answer is no. So let's take a look at the next set. What can we learn from this ratio of these numbers that we get? So looking at the KEQ values, one can determine which side of the reaction is favored at equilibrium. So a small KEQ means that the reverse reaction or reactance is favored. Another way you can think about it is the reactance is more than the products at equilibrium. For a large KEQ, the forward reactions or products is favored. So what does that mean? It means in this case, the products are greater than the reactants at equilibrium. Okay? Now, KEQ changes only with a change in temperature. Why? Remember, temperature changes the fraction or percentage of effective collisions. So if KEQ is based upon the ratio of products to reactants, the only thing that will change that ratio is a change in temperature. Now, going back to reaction kinetics, you might say, well, why not concentration, Mr. Chan? Because recall, concentration, even though you have a large, with a higher concentration, you have more effective collisions, you also have more ineffective or not effective collisions. Remember, temperature is the only thing that will change the number of effective collisions, okay, or the fraction of effective collisions. Now, Notice in the previous example we gave you, I gave you the equilibrium concentrations, okay? And all we did was we plugged it in. But what if we don't have the equilibrium concentrations? One can determine the KEQ values when the values are not in equilibrium by using something called ICE tables, okay? Let me give you an example. It says for the reaction, N2 plus H2 gives you 2 NH3. The initial concentration of N2 is 0.32. The initial concentration of H2 is 0.66. At a certain temperature, the equilibrium concentration is found to be 0.3. Calculate the KEQ. So in this particular case, the only thing that we're given is the equilibrium concentration of H2. Okay? But notice we're not given anything about NH3 or N2. So how do we approach a question like this? So we have N2 plus 3H2 is in equilibrium with 2 NH3. Now, what do I mean by ICE tables? So what we do is we set this up a little bit. How much space do I have? Oh, lots of space. Okay. So we set this up. So we have the initial concentration. We have the change in concentration. And we have equilibrium concentration. This is where we have ICE, I-C-E. Now, in some books, they even put it as rice because they say this is the reaction. So this is where we have rice tables, okay? Now, so where do we fill in this information? So it says here, we have the initial concentration of N2 and initial concentration of H2. So what we have here is this will be 0.32. This is 0.66. So I'm just going to highlight it in green just to identify the numbers. Now, we're given the equilibrium concentration of H2 is 0.30. So 0.30. And I will highlight it in yellow. Okay. Now, how do we fill in the rest of this table? Okay. Now, a couple of things. Notice in the question, they did not give us any information about NH3. So how do we start this off? We'll call this 0. So assume 0 because no info. We weren't given any information on this. Now, the next thing is, where is the change? Now, so some of you might say, oh, Mr. Chan, the H2 went down. It went down 0.36. Because how did we figure that out? To go from 0.66 down to 0.30, it must have went down. Yes. Okay, now since nitrogen is on the same side as hydrogen, this will also go down. And the NH3, because it's on the opposite side of the equilibrium arrow, it's a product, so it must go up. So in this case, both reactants went down. And because the reactants went down, the product went up. Now, another way you could think of it is this. The products had to go up because you started with 0. There's no such thing as negative concentration. You have to have a positive concentration. So if you start off with 0, there's no choice but for the concentration to go up. Now, how much did it go up by? In this case, here went up by 0.24. Here it went down minus 0.12. Now, how do we figure this out? Is because what you have is mole ratio. Remember, it goes back to graphing. Okay, remember the changes have to follow the mole ratio. Going back here, the reactants went down by 1 block. This one went up by half a block because of the mole ratio. All right. So if we take a look, my calculations. Now we can fill this in. This would be 0.20. This would be 0.24. Now we have our equilibrium concentrations. We're good now. Okay, we figured it out. And then all we need to do is just plug it in. So we have KEQ is equal to concentration of NH3 squared, concentration of N2, concentration of H2, all cubed. And then what I get is I just plug the numbers in, 0.24 all squared divided by 0.20 and 0.30 all cubed. And if we plug those numbers in, we have 0.24 all squared divided by 0.2 divided by 0.3 y to the 3. So the answer would be 10.7. Okay. Now, this second part where we plugged in the equilibrium numbers, it's exactly the same as the worksheet that I just did here. You just plug in the equilibrium numbers. There's no difference. The only thing was, in this question, I gave you the equilibrium concentrations. Here, using the ice tables, you had to figure it out yourself. Okay, that is the only difference. Okay, in terms of here, you had to figure it out before you plug the numbers in. Okay, all right, what I'm going to do is I'm going to go over one more example and then we'll stop the video. All right, and what I want to do is I want to take a look at question number 10. Okay, it says if 0.2 moles of HCl were placed in a 5-liter flask and allowed to come to equilibrium shown below, what will be the equilibrium concentration? Now, the key thing is this. Notice the word, it says allowed to come to equilibrium. Because it says it's allowed to come to equilibrium, that means that this 2 moles in a 5-liter flask is the initial concentration. Again, you need to take a look at the wording and that will help you out. Okay? So if I were to do this question, so question number 10 here. So I have 2HCl is in equilibrium with Cl2. Is it Cl2? H2 and Cl2. Okay. H2 and Cl2. Now we set up our ice tables. Okay, so we set up our ice tables. Now, how do we fill it in? It says 2 moles of HCl. I'm going to highlight it in a different color. 2 moles of HCl are placed in a 5-liter flask. Now, so here, the initial concentration would be, let me get a pen here. This would be 0.40 molarity. Now, remember, when we're doing equilibrium or ice tables and stuff like that, we have to use concentration. So the first step you should always do is take a look, is it concentration? Now, if we go back to the original question, they don't say anything about the initial concentration of hydrogen or chlorine. So here we go 0, 0. Now by default, again, this should be minus, this should be plus, this should be plus. Again, if you're not too sure, you can stop the video here and try to figure out why is HCl minus, why is H2 plus, and Cl2 plus as well. Okay. Now, in this case, what will the equilibrium concentration of H2 be? They don't know that. So going back to math, if you don't know what something is, what you use is you go fill in with x. So this would be x. So this would be plus x. This would be plus x. This would be minus 2x. Again, because of mole ratio. So this would be 0.40 minus 2x. Here would be x. So again, you have your equilibrium. Okay, you have your equilibrium concentrations. Now all we do is we just plug it in. So we go KQ is equal to concentration of H2, concentration of Cl2, divided by concentration of HCl, all squared. So the KEQ, if we look, is 5.32 times 10 to the negative 4. So was it 5.32? Sorry, 3.2 times 10 to the negative 4. So this would be 3.2 times 10 to the negative 4 is equal to x squared all over 0.40 minus 2x all squared. Now, at this point in time, some of you might say, oh, damn, do we have to do quadratic? Okay. Now, for those of you taking Chemistry 12, the answer is no. For those of you who are planning to take AP, you might need to do some quadratic, okay? But what I'm going to do is I'm going to focus on just the Chem 12 material. Now, in my tests and stuff like that, you will not need to have to do quadratic. Well, so what you can do is this, to simplify it, what you can do is you just take the square root of these values. And so if I took this e negative 4 square root, oopsie, square root 3.2 e negative 4. So here, if I take the square root, this would be, oopsie, 0.0179 is equal to x all over 0.4 minus 2x. So you have 0.0179, 0.4 minus 2x is equal to x. And you remember from your math, you know, the FOIL, whatever that thing is. And then you solve for x, okay? And x will be whatever number. Okay? That's about as complicated a math in terms of KEQ that you will get in regular Chem 12. In AP 12, you'll probably have to do quadratics. Okay? But notice the setup is exactly the same. We had to find the equilibrium concentrations, whether it's a value of x or whether or not we're actually given values. Notice the similarities. We had to follow the mole ratio to find the equilibrium concentrations, and then we plug it in, and we do the exact same thing here. Come on, where is it? You had to fill in the ice tables using mole ratio, and then in this case, you solve for X. All right, ladies and gentlemen, that is it for this KEQ introduction. The next lesson is I will be talking about temperature in KEQ and trial KEQ. All right, folks, thank you. Have a good day.